Hello everyone. On this occasion, I will explain about my research entitled Sensitive Similarity on Programming Assessments Expecting Highly Similar Submissions. I'm Oscar Karnaling, and I'm from Maratha Christian University, Indonesia. So first of all is the introduction. Some programming assessments expect highly similar student submissions, adding complexities in detecting plagiarism. There are a number of automated similarity detectors dedicated for such assessments. However, they either are not practical, being integrated with a programming workspace, or might be less effective because it relies only on subtle variation. So, as a contribution, we present sensitive similarity. It is a combination of syntax and superficial similarities. Superficial similarities is calculated by converting student programs to token sequences with neither comments nor white space and comparing them to each other. Syntax similarity is similar to the superficial one, except that the token sequences are further pre-processed. Any identifiers, constants, and data types are generalized to their types. Sensitive similarity prioritizes programs that are similar at both syntax and superficial representations. So we have two research questions with the development of sensitive similarity. First, is sensitive similarity more effective than syntax similarity for identifying copied programs in assessments expecting highly similar submissions? The second one is sensitive similarity less time efficient than syntax similarity. Why? Because, of course, it considers more aspects in calculating similarities. So the method, first, the submissions are tokenized with the help of ANTLER. So basically, the detection covers three programming languages, Java, Python, and C#. Both submissions token strings are then compared twice, one for measuring the syntax similarity, while another for measuring the superficial similarity. For the syntax similarity, the token strings are further processed. Any identifier names, constants, and primitive data types are generalized to their corresponding token types. So measuring syntax and superficial similarities are essentially the same, and there are five options of algorithms. First is running Kaprabi graded string tiling. Second one is Minhash, Superbit, Jacquard, and Cosine. Syntax and superficial similarities are normalized by doubling the number of match tokens and dividing the number with the total number of tokens for both programs. Sensitive similarity is obtained by averaging the resulting syntax and superficial similarities. Our approach is integrated to SRange, an automated similarity detector. So how we address the research questions? Both research questions were addressed based on code submissions on our software design pattern course. So the course covered 22 common design patterns implemented in Java. Each design pattern was covered in one lab assessment at which students were instructed to submit 2 Java programs. A design pattern example taken from the internet, and an adaptation of the example to their own case study. So in total, there are 610 programs. Per assessment, each student program was considered as one independent submission. Any programs that were taken from the internet were checked manually by the instructor. Programs from the same internet source were paired one another and then flagged as copied with the internet source one. So RK1 was addressed with top K precision, where K is the number of copied program pairs. Assessments with highest and lowest top K precision would be qualitatively analyzed. And for the second research question, it was addressed by time required for calculating top K precision and generating the similarity reports in nanoseconds. So this is the findings. So sensitive similarity appeared to be more effective than syntax similarity. The top K precision was substantially higher by 11 to 18%. It can be seen in the table here. And the difference are statistically significant. On RKG-RGST algorithm, the assessment of the iterator pattern was the most favored by the sensitive similarity. The top K was improved by about 46%. Why? Because the implementation of the iterator pattern would be the same regardless of the case study. Assessments about comment and proxy patterns were also the most favored by the sensitive similarity. Students use the same structure from the copied code and only put minimum changes in the identifier names. So these are the results. Comparison between syntax and sensitive similarities in top K precision for all assessments. So we have 22 assessments in here. So when RKR-GST was replaced with MinHAS, the top K precision was lowered, like reduced by 8%. Why? Because MinHAS did not consider the whole token sequences, and it might mistakenly put copied programs on different clusters or groups. The reduction occurred on some assessments, including those of decorator, factory, and proxy patterns. Superbit algorithm resulted in comparable top K precision with that of MinHAS. Superbit algorithm favored assessments of comment, memento, and proxy patterns. Jacquard algorithm showed comparable improvement in top K precision, but its top K precision for the syntax similarity was a bit lower. On several assessments, improvements introduced by sensitive similarity become smaller. Unlike MinHAS and Superbit algorithms, Jacquard did not have the token strings. Cosine algorithm was as effective as Jacquard on the syntax similarity. However, sensitive similarity further improved the effectiveness, making the performance comparable to the remaining algorithms. Larger improvement was consistently found on many assessments. Why? Because Cousin algorithm considered token occurrence frequencies, but with no hashing techniques. So the second research question is about efficiency. So sensitive similarity exclusively considered superficial similarity in the calculation. Thus, it was expected to result in longer processing time. Although the changes were statistically significant, they were not substantial, except for RKR-GST. Other algorithms had linear time complexity, and calculating the superficial similarity did not heavily affect the processing time. When observed per assessment on RKR-GST algorithm, sensitive similarity took the longest processing time on the assessment of memento, visitor, and bridge patterns. Student submissions were considerably large on those assessments. For other algorithms, the findings were somewhat consistent, except that the changes were far less substantial. Locality-sensitive hashing algorithms did not seem to be faster than their base algorithm, Jacquard and Cosine. The finding might be different or larger submission. So as the conclusions, this paper presents sensitive similarity, combination of syntax and superficial similarities. It is more effective than the syntax similarity, although it is a bit slower. The performance of sensitive similarity is affected by the selection of similarity algorithm. RKR-GST seems to be more effective, but takes longer processing time. MinHAS, Superbit, Jacquard, and Cosine show relatively similar performance one another. So there are three limitations. First, while top K precision is a reliable metric, the effectiveness of sensitive similarity can be further confirmed by other metrics. As the evaluation was performed on a small dataset, processing time might be affected by hardware and operating system. Conducting such evaluation on larger dataset might be useful. Third, we have not compared our approach to other similarity detectors for assessments, expecting highly similar submissions. Future work might focus on such comparison. Thank you.